so yesterday we went over what a piecewise function was. Does anybody need a copy of the handout? Oh, you do. So, absolutely, you want to watch the first video. Okay. I'll try to get it from somebody else. Okay, so, K of x. How many pieces does K of x have, you guys? How many? 2? What's the first function?
4 cosecant of 2 pi over 3x plus 2.
So we got a fairly complex trig function. It's not that bad because it doesn't have a phase shift, so it shouldn't be too bad. Let's see, and then the other one, what kind of function is this part? Exponential decay that's been shifted.
Right 6.
Minus is right, yeah? Right 6, there you go. Okay. So first, I think I asked you to plug in some things and then we'll graph it. So that's what we'll do. So I'll try to graph it like down here. Let's see. Well, I don't know. Let's graph it over here. When we start graphing it, where are we going to kind of definitely want to focus on in terms of the domain of the graph? You're definitely going to have part of the graph. Where's like the division between the two functions on this one?
6.
It's at 6. So I'm thinking we're probably going to want to put 6 kind of right here in the middle so we get that function after 6 and we can clearly see enough of the cosecant before 6. Okay, so maybe I'll scale it by 3s. I'm not sure yet. As you guys work on your next worksheet on this assignment, which you'll probably do for the most of the rest of this week, at least tomorrow, you definitely want to do a rough draft and a final draft on these. Don't just try to do the final draft right away on your worksheet. If you do, I'm guessing you don't have nearly enough experience to get it just right the first time. So you're going to want to do a bunch of scratch work on another sheet of paper, kind of get down the different edges and so forth, and then compose a final draft on your worksheet. Does that make sense to you guys? If you don't follow those suggestions, I don't think you're going to be able to do this. So make sure that you do like a rough draft and a final draft. Okay, I think I only gave you like 6 problems as your homework, so it's not very many problems. Okay, so let's see. We're going to try to follow my directions once we start graphing, but what did it ask us to plug in? I don't know, I'll just pick some values. See if I pick some ones. Did I say plug in 6 to K? And I think I said plug in like 1.5. And I think I said plug in like 0. Okay. And then, did I say 9? All right, let's just do some of those ones. That's probably good enough, okay? Because we could pick anything. So if I put 6 in, which one of these does it go into? It goes into this one because it's equal, right? Did I get that right?
Yeah.
Okay. So I'm going to put it right there. So that's going to be 4 cosecant 2 pi over 3 times 6 plus 2. If you're feeling pretty comfortable, you probably don't want to do too much scratch work. This is feeling like too much to me. I would just think about 6 goes right here. You could either say that that's 12 pi over 3 then, or you could say what's 6 over 3 reduced to?
4 pi.
2, which then times 2 pi is going to be
4 pi.
4 pi. So if you want to skip that step, I would probably recommend that. I would never have written this down for myself. It's up to you though. So 12 over 3 is 4, or 2 times 2 is 4 pi. Okay, that's a unit circle calculation. So whether you do it in your head or not, I'm thinking this one we probably can't do in our head. Some of you probably can if you know how to count your asymptotes by now. So like, let me think, since I did this with a couple people this morning who could do it, how would you do this in your head? Cosecant goes with sine. Sine starts waving right here, right? So the first asymptote for sine is right at the origin. The next one's going to be the next x-intercept, which is where? That's the last x-intercept. Sine goes like this, doesn't it? So it's going to be 0, and then pi, and then, so what's this going to be?
Undefined.
Undefined. Even if you put undefined plus 2, it's still undefined. because that's going to be on an asymptote. I'll do the x one without doing it in my head. Okay, but that's the goal we should be shooting for right there. That's how you make this easier for yourself. Okay, next one. I'm plugging in 1.5 this time. Which branch does that go into, 1.5?
4 cosecant.
It's less. It's still going to go in the cosecant. Okay. Let's try to do it a little nicer this time. So if I put 1.5 right here, that doesn't reduce real nice. What's 1.5 times 2 though? So 3. So we have 3 pi over 3. What's 3 over 3 though?
1.
It's just 1. So I can just say this is pi. That's pretty good work right there. Oh, and we just decided a second ago that, did pi have an asymptote?
Yes.
I think it did. So let's pretend you didn't do it that way though. Let's pretend they were like on the unit circle quizzes. And you're like, okay, where's pi? All right, pi is over here, right? So -1, 0. Cosecant goes with sine, and sine is the y value. So if I flip 0, I get undefined. The fact that I'm adding 2, again, does not matter. So that's another asymptote when I go to graph it over here. In fact, I could just start doing that right now. So at 6, we've got an asymptote. And at 1.5, we've got an asymptote. I hope that when we start graphing it, that matches up. Yeah? All right. 0, if I plug 0 in, I think I'm still here, right? So that's going to be 4. When I put 0 in here, it's going to wipe that out, make it 0. And I think a second ago we just decided there was an asymptote at 0. If you want to confirm it like this, do it. This is also undefined. So I've also got an asymptote at 0. Crazy. 9. Now I'm finally greater than 6, so I can be on the exponential decay function. Okay. So I'm going to go 0.9, plug 9 in, 9 minus 6 is 3. And you know, you might need to go to your calculator on that, unless you know your power tables really well. What's 9 cubed? Ah, a lot of you guys know them. Very nice. 729, so what's this? 0.72. That's some sweet stuff. You can go to your calculator on that one for sure though. Okay. All right. So let's try to graph this guy. So those are the values it asked. So on the other side, like I said, usually you're going to want to use some scratch paper. Yeah, you guys? Oh, do you want me to do -3 real quick? I'm going to leave -3 for you to do on your own, okay? So I'm going to leave that one. Thank you though, Colton. Okay, so let's try to follow my process. Step 1, look at the first piece and just draw it and worry about this afterwards, right? Philip?
So what would the +2 do to that?
I think that's exactly where we're going to have to start right now. You guys, what does that +2 do to the function? It's going to shift it up 2. It didn't really have an effect on these ones because they were undefined though, right? That's what Philip's asking about, aren't you? So I think if you're on an asymptote, does it matter if you're shifted up? No, that's the reason. But we're going to use that right now to draw it. So up 2. Let's put Philip's asymptote in. So about right there, I'm thinking. It's not really an asymptote, but it's kind of a guide. At y equals 2. I think I'm going to draw the actual function today in red. Okay, so the actual function we're going to draw in red. And then Thursday, I think we'll take some time and use Grapher on our computer to confirm our answers from the homework. Okay, so it should be pretty fun. The actual function is going to be in red. Everything else is just guides. All right, so let's see. So we went up 2. How much up and down from that is it going to go? 4. I'm going to get rid of some of this now so clear up some scratch space. So I'm going to need to do some scratch space. So my amplitude on the sine wave is going to be 4. What's its period? Sine starts with 2 pi. And I divide by that. So you flip. Period's going to be 3. Okay? I made it that way because I cooked this problem to look nice. What else? I think that's about it. Should be good. So if we draw the sine guide, we're going to start at the origin or up or down?
Origin.
Origin, but this is the new origin. right? How far up am I going to go? Up to 6. I'm going to go down to -2, and I'm going to sine wave. And when am I going to be done with my first wave? At the period. So I'll be done right here, and right in the middle, I'll be right there. So I'm going to go up and down. And we could just keep drawing this. Where do we want to think about drawing this, though? Go back and look at your piecewise location. So I want to draw this one if I'm less than 6. So I should go all the way up till 6. So I got to go one more period, right? So it'll end right there. Go up and down. And then I should just keep going this way forever, so let's just draw one more that way. So go down, there we go, and up. That's big enough. Okay, it's going to keep going to the left. But that's not the actual function, right? To draw a cosecant, I got to put the asymptotes. Look, does this one look right? We put in earlier. So does this one, right? And there's going to be another one which we didn't put in right there. And one at 4.5. Should probably label that one because it's a little unclear. That one's clear at 3. I'm not going to label it. I might label this one. You guys see how I'm going with the labeling now? We're kind of adults and can judge these things. This one, I might need to label. That one, I don't need to label. And I said I'd draw the actual function in red. So the actual function's going to have like a piece over here, a little pseudo-parabola, right there, a little one right here, a little one right here, a little one right here. Gonna watch out, I'm getting close to where I'm supposed to stop, right, at 6. So I think I'm gonna have one more in here. Am I gonna have this whole parabola, or just part of it, or what?
All of it.
I think all of it. It's gonna stop right up next to that edge where we're supposed to stop. Does that make sense? Okay, so we're done with the first piece. We've only got one more piece, we'll be done. So this guy is an exponential decay function, so that means it's going to have a shape that looks like a decaying curve. When it decay curves, unless you shift it up or down, which this one's not, right? We said it was just shifted. I guess we could write it down right here. Right 6. It's always going to have an asymptote at the origin. And normally it would go like right through 1 higher than the origin. I think we talked about that again yesterday. But where's it been shifted now? To the right by 6. So I think I shifted it right by 6 to make it kind of match. Yeah? So instead now it's going to be like over here. And if you follow the instructions for graphing, I think that we probably really need to plug in the edge on this one. This one we didn't need to plug in the edge. Why? We kind of had the graph right up to that edge, didn't we? So I don't think we really needed the edge on that guy. But this one, I'm not really sure. I'm not exactly sure. You guys might be sure, but if you're not, plug in the edge. So I'm going to plug in the edge. I'll get 0.96 minus 6 is 0. What's anything to the 0 power? 1. So at 6, this guy is 1 right there.
Open.
And then it's an exponential decay. Erlen's already telling me, hey, it's supposed to be an open circle, right? And exponential decay would go like this. So I think it's going to go and approach that asymptote. And I'll probably label this edge as 6, 1. And I'm done. Okay, so there's another example. I will do beta this afternoon and put that on this same tape. Okay, so this will be Piecewise Trig video 2. Definitely want to use it when you're working through yours if you're having trouble. Okay, let's look at that last. Do you have a question?
Yeah, does that side continue?
Does this side continue? Excellent question, Ms. Shaker Scott. What do you guys think?
Yes.
Do the pseudo-parabolas keep going like this? All the way to infinity. Yes, ma'am. Does this side continue with the exponential?
Yeah.
Yeah, clearly. It's just kind of hard to show that this continues. I guess if you really wanted to be nice, You could go like that, right?
Yeah.
Something like that would be easy. Good question. All right. Before I erase this, let's jump to part 4. And let's do part 4 for this graph. And ironically, this is the only one I want to change when I made this up. So you guys see part 4? Average rate of change. So this was an idea they had on Park a whole bunch. I should have covered it earlier. Oh well. The average rate of change is another way to describe, I think we talked about this already. Slope, okay? So it's the slope, but it's the slope between two specific spots on a function, because clearly this piecewise function, it doesn't have a uniform slope. It's not linear, right? Like if I look at the slope between here and here, or between there and there, or between there and there, it's going to be totally different in every different spot. But this is the idea, again, of changing things to movement, which is what calculus is all about. So it's a nice idea to start playing with just a bit this year. So we're going to find one average rate of change for each function. So we're doing k, so let's go to number 3. I want to change the interval because my interval is screwed up. Can somebody look at the interval you have on your page and tell me why it's screwed up? Look at our picture. Think about why my interval was a bad choice. It says go between -3 and 1.5.
They're on completely different pseudo-correct lists.
I think you can do that, though. It's a good idea, though, Dennis.
Those are
-3 is on an, and that would be bad enough, but also 1.5 is on, it's not even on the function, so if you tried to do slope, you'd be like, do I go from like here on the asymptote to there, or it'd be undecidable. Does that make sense? So I gave you an impossible one, all the other ones work. Let's change it to the interval -0.25 to 0.75. Okay? And we'll do that one.
Can you say that again?
Yeah, I'm going to write it up before. So we're going to find the average rate O change. And we're going to do so on the interval -1/4 to 3/4. Okay. Now if you look at your graph on that one, you can use your graph to actually just do this. I'm going to do it both ways. Okay? I'm going to do it with the graph and without the graph. Okay? All right, so let's just draw it on the graph first just to see what this looks like visually. So I'm saying, what's the average rate of change on the actual function from -1/4 to here? So where's -1/4 hit on the function? So this one was at -0.25, -1.5. So where would -1/4 be on there? This would be like negative, what would be like right in the middle here? -0.75, so it'd be somewhere like here-ish. Does that kind of make sense? Something like that. Not exactly sure. Something like that. And then to 0.75 would be like where? This is 1.5. See how why the labeling really matters here again? That's 1.5. What's right in the middle of 1.5? So it'd be like right here, exactly, right? So when I find the average rate of change, I'm looking at this line. So it's going to be a pretty steep slope, right? Looks pretty darn steep. So I'm hoping we get a pretty steep number when we do it. Okay, let's see. So if I do average rate of change, that's like rise over run. It's just like slope. So I'm going to use, which function am I using for both of these, by the way? I'm using the cosecant function, right? And I'm going to do it like this. I'm going to go k of b minus k of a over b minus a. There's all kinds of symbolic ways to do this. This is the one you would use in the future. So b is like the end spot on the interval, and a is like the beginning spot on the interval. I think in the past you called them like x1, x sub 1, and x sub 2. Okay. So if I plug b in, if I put 7.75 in, what do I get? That's 4 cosecant 2 pi over 3 times 0.75 plus 2. And then I've got to subtract, this is going to kind of get ugly, 4 cosecant 2 pi over 3 negative 0.25 plus 2. Holy moly. And then on the bottom I'm going to have 0.75 minus a negative 0.25. So the bottom's real nice. Minus minus is plus, that's going to be 1. Okay? On the top, we could do this with or without a calculator. I'll do it without one. You could totally put that in your calculator. I'd be fine with that this time. So if I put 0.75 times 2, what is that? 1.5? Nice. So we got 4 cosine, I'm doing scratch work, of 1.5 pi over 3 plus 2. What's 1.5 over 3? 1/2. And that's a unit circle calculation, which I can do. So this is up here. I've got 0, 1. This guy goes with sine, so it's going to be 1. 4 times 1 plus 2 is 6, just like we knew already. So see, we could have used our graph to help us on that one. So this guy is what? 6. We've got 6 minus. That was kind of a lot of work. So let's use our calculator to do the other one. Okay, why don't you guys type that in your calculator right there and see what you get. Everybody needs to try it. Oh, and this is one you guys might not know how to put in your calculator, so you might want to watch up here. So I'm going to sneak this over here if we can get it in the video a little bit. We've already got that the slope should hopefully be pretty steep, so I'm going to erase our graph so you can see this in the video. So how do you put cosecant in your calculator? I don't think I've shown you that yet. You guys probably figured it out though. Any ideas? There's no cosecant button. You put it in the sign and then flip it or something like that. Here's how you can do it. So I'm going to go 4 times, and then you could put in a fraction. So if you have an 83, you're just going to have to use parentheses. And we're going to go 1 over sine, because that's what cosecant is, 1 over sine, right? And we're going to put in, I'm going to put in another fraction. If you've got an older calculator, use another set of parentheses. Put in my 2 pi over 3. And what were we plugging in on this one right here? It's kind of hazed out here. We were trying to plug in negative 0.25 to begin with, right? So times negative 0.25. Is that it?
Let's do.
No,
Plus 2 here?
Yeah.
no, on the outside.
Think about your equation up here. Isn't the plus 2 like totally outside? I think that we better make sure we put it totally outside. Okay, so the video got cut off there for a second. So I was just going to finish up this rate of change example, so I did have to erase the graph, but we're still working with that third function, k of x, with the cosecant and the exponential decay pieces. We were calculating the average rate of change on the interval from negative 0.25 to 0.75, which are both within this piece. Some of the ones that I gave you average rate of change on, you'll have to use like one piece on one edge and one piece on another edge, so make sure you look at those subdomains to make that decision. And there'll be another one at the end of this video as well. Okay, so to do that, I think we go whatever the function evaluated at that one is minus the function evaluated at that spot. That's going to be the rise, because those are y values. And then on the bottom, we've got the run, so I've just got the Okay, so on the bottom we've got the run, so I've got just 0.75 plus 0.25, so that's just going to be 1. So we'll do these on the calculator. So I'm going to go and say 4 times, and I'm going to have to enter cosecant. There's no cosecant button. So the way you do that is you use the identity that says it's 1 over sine. Cosecant is 1 over sine. And then I'm going to plug in exactly what it says. I've got 2 pi in there over 3, and I'm going to put 0.75 in for x. And then I'm going to put my plus 2 on the outside because that 2 right there is clearly outside the function, so it shouldn't be on the bottom. So I get 6 for that. So that one's going to be 6. Then we've got minus, and I'll do this one. If you're smart, you're going to want to use the second entry button, and then all you have to change is this part in here, negative 0.25, fix your parenthesis, and there you go. We've got negative 6. So that's going to be what? Positive, so 12 over 1. So the average rate of change on that subinterval is 12. And if you go back and rewind or look at the graph, just remember what it looked like, it makes sense that it's really steep because it was rising quite a bit. In fact, 12 for every run of 1 on that one. Okay, we'll do one last example here in a second. Okay, so first on the front side of that worksheet, it asked you to plug in, I think these were the values. If I missed one, that's okay. Okay, I kind of made them up. JJ, put it away. Okay. So first we're plugging in 2. What do you guys think? Which piece of the piecewise function should we be looking at if it says put 2 in?
Yeah, second to last.
Second to last, I like it. This one, logarithm. So we're going to go log of, what, 4 minus 2 is the log of 2. What's the base of the logarithm if it's not specifically noted? It's 10. I don't know 10 to what power is 2. I don't know what that is. I'm going to have to use my calculator. You guys put it in your calculator. Tell me what that is. What is log base 10 of 2? Quick. I got about 0.301. That makes sense that it's less than 1, because if this was 10, the answer would be 1, right? 10 to the 1 is 10. So it makes sense that it's less than 1. Okay, if I put in 0, what do you think, Mr. Gukin? Where would 0 go? Which piece would I be using of the 4 pieces? I know, Brady, you know how to do this part already. Thank you, though.
Probably the top one.
No,
Why not?
there's no 0 in there.
It's not the right answer.
This is just less than -5. This one or this one?
I think it's the negative 5 one.
It's this one, right? Because it's equal right there. So we're going to put it on that one. 2 cosine. If I put 0 in, everything inside will become 0. And you guys, 2 cosine of 0, what is that? 8. Oh, okay. Yeah, I'll be here. Okay. I'll be here for sure. Okay, so cosine of 0, 0 is the angle that's over here, and the x value of that angle is 1. So this is 2 times 1, or 2. Okay, -7, I think that is less than -5. So I'm going to put it in the parabola.
Sure.
So -7 plus 3 squared plus 6. Watch your order of operations here, real easy to mess up. Let's go inside parentheses first. That's going to be what, -4? Square -4 and you get +16, but then there's another minus outside. So I think that is -10. Okay, and then -2.5 I think is again here. So we're going to go 2 cosine. We're going to be a little bit careful here. So I'm going to think about this as 2.5. You could go 2.5 over 5 and reduce that to 1/2. Or you could say multiply across the top, right? There's different ways to handle this. Let's multiply across the top. What's 2 times 2.5? 2 times 2.5 is 5, and it was negative, so negative 5 pi over 5. Because I didn't touch that 5 yet. And those 5's cancel, right? So this is just negative pi. I might need to draw a unit circle thing on that one. Negative pi is over here. Cosine is the x, so I get 2 times negative 1. That's going to be negative 2. Okay? Yeah, thanks, Bryce. Thank you. All right, so let's start trying to graph this guy. That's the main thing to do. So I'm going to erase this stuff. Oh, 10. I didn't do 10. If I put 10 in, that's clearly bigger than 4, so I'd get 1 over 10 minus 4. That's a 6. Okay? So that's it. So there's plugging in. What if we need to graph this? Remember, you want to follow your directions. Step 1, look at each piece individually, draw it, and then look at the edge and plug in the edge. That's the idea. So the first piece is a parabola. You guys tell me what's special about this parabola. Where's it been moved?
Up 6.
Up 6, yes?
And left 3.
Left
No,
3.
right, yeah.
And flipped over. So like up 6, about right here. Left by 3, so the vertex would be like around right there, right? And it's going to be facing down. So it would be something like this.
Katie Zarella and Kaylin Billy to Student Services.
You can draw a quick sketch, but my suggestion would be just draw a quick sketch. When you're actually doing this on your worksheet for the next 2 days, because I think I gave you guys 6 problems to do on Wednesday and Thursday, there's only 6 problems. You're going to want to do a rough draft and a final draft. See, I don't know exactly how big this parabola is opening, so it's really a rough draft right now. I'm going to probably be doing some erasing. Anyway, step 2 is you look at the edge and you plug in that edge. So I only want the parabola when it's less than negative 5. So I'm going to plug in that edge and go like this. So I think I'll get negative 2 inside. That becomes 4. And 6 minus 4 is 2. So at negative 5 right here, I'm too high. So actually my sketch isn't too bad. What do you guys think? Am I supposed to be filled in or open at that edge? Filled in. My sketch wasn't too bad actually. So there we go. I'll keep the rest of it, okay? And then step 3, you erase the part that doesn't count. You guys tell me, do I want to erase the left side or the right side from that edge?
Right.
I only want this function when it's less than negative 5, so I don't want this. Okay, done with piece 1. Then you just keep doing it for the other pieces. So the second one, I've got a cosine function. Oh, I might need to do some scratch work on that one, definitely. It's pretty simple cosine. 2 is the amplitude. Help me with the period. How am I going to get it? Divided by that stuff. Flip. Oh, nice. Cancels. So the period of this guy is 5. I built it that way so that it would do some nice things. So it's going to be waving every 5, 1 full wave. Okay? So I want that between negative 5 and 0, kind of like right here. And if you think about your cosine, we usually would start it where? It starts in the middle, up or down? Starts on top. How high does this one go though? Amplitude's 2, so I'm going to start up 2, and I would usually at 5 I would end up 2. But am I going to go over here? You could do that and erase it if you want, but you're going to be erasing. I only really want to hit this area, right? So instead of going that way, I'm going to go this way. Oh, nice. This one's going to connect up, isn't it? And then in the middle, what's the middle? 2.5? It's like 2.5-ish. It's supposed to be down 2 and wave it. Something like that. Connect it up. Okay, so that one happened to connect. There we go. Next one. I don't think I have to do anything about this edge. It's pretty darn clear where the edge is, right? So I don't have to worry about plugging in the edge. Should it be closed though?
No. It's not equal to. Yeah.
Why is this one not open? It says open right there.
Because the top one's connected.
They connected and the top one is nice. Good. Okay. All right, next one, logarithm. It's been a while since we've graphed a logarithm, so let me help you out with that one definitely. This guy, something you've learned from doing a bunch of trig should be you should automatically do something
Excuse me for the
inside.
interruption. I need the following
What is that
students to
thing?
the stage at this time. Devin Dawson, Brooke Holmes, Alyssa Griffith, Rebecca Kiefer, Kira Arnold, Zoe Harris, Rachel Badula, Anna Slade, Veronica Bond, Cole Ross, Elise Scott, Hannah Destiny, Tanner Houghton, Shu Takamatsu, Raven Langosh, Carly Newitt, and Nia Prescott. Thank you.
Haven't we been doing this with trig whenever there's a phase shift? Whenever you see something like that, it should be your instinct to factor now. Those share a 2, don't they? So what's left? X minus 1. So this is the logarithm shape that we, I think, reviewed yesterday briefly, and it's been shifted where? Right by 1. That logarithm shape goes like this, so it's been shifted to the right by 1. If you remember, the logarithm has a nice asymptote at the beginning, so I should have that asymptote now to the right by 1. Okay? And if you remember your logarithms, just like exponentials, they go through, ladies, they go through either 1 above or 1 to the right. So this should be a 2. And I'm going to logarithm it. So from down here, it's going to keep going up, and it would just keep growing, except we're going to chop it off at 4. So I need to plug that edge in and find out what happens. Okay? So if I put 4 in, I get log of, what, 8 minus 2, that's log of 6. Again, I think that's going to be less than 1. We need our calculator. What is that? You guys tell me.
0.779.
Okay, either one. We're just kind of going to guess, right? So I kind of made this go too high. At 4, it should be a little bit less than 1. An open or closed circle, what do you guys think? Closed. So something right there. Logarithms actually grow pretty darn slow. And I'm going to label this edge because it's really not obvious where it's at. Okay? And the last piece, we're just going to have our 1 over x shape. I think we reviewed that again yesterday too. This one's been shifted where? What's that minus 4 do? 4 to the right. And coincidentally, this is also 4, because I made it that way, so it'd be nice and easy. Okay, so I think I want an asymptote right at 4. And the other one's right here. And then you've got like a piece like this, and you've got a piece like this, if you remember your 1 over x shape. Except, do I want this piece? No, I just want the piece that's bigger than 4. So I just want this piece. And now if you want to, you can get rid of those asymptotes. They're kind of freaking your eyes out or something, but we're done. Okay? So there's our function. It's got nice 4 pieces. It connected here, didn't connect anywhere else. That's it. So last thing, we want to look at average rate of change. So I'm going to do the average rate of change on this one since we've got it drawn. Okay? So I asked you a specific interval. You guys see at the bottom on part 4? There's a blank there. Can you guys help me fill in that blank first? Slope. Slope, yes. Average rate of change, remember, is slope. It's just the slope between any 2 spots on a function. So I could have asked you between here and here. Like here and here would have been like a positive slope. There and there would have been like a negative slope. Here and here would have been like a 0 slope. I could have asked you anything. I just kind of picked something out of the blue. Okay? So the interval I asked you was what? -7 to -2.5. So let's do that one. So the average rate of change. It's not really a good way to abbreviate it. If you just want to write average, it's fine. Okay. So it's slope. So it's like rise over run. All right. And the interval I asked you to do it on was, what was it? -7 to -2.5. So if you have the graph, like we do, we spend a lot of time making this graph nice, you can just kind of eyeball it on the graph. That's not really good enough for any purpose in the world, but it gives you an idea. So -7's like right here, so it's going to be somewhere down here, right? Like maybe on the tip of that arrow, it's going to keep going. Maybe right there? And then -2.5, wasn't that this spot? I think it was. So what do you guys think? The slope on this is going to be positive. My picture might be off, so steepness, I don't know if it's right or not. Okay, my picture's not perfect, so we'll see. So here's how I'm going to do that. I'm going to do the y values on top. So I'm going to do the y values first. So the first, let's see. So I'm going to go beta of this guy minus beta of this guy. That's the y values. That's the rise. And then the run is going to be, well, the x values. So the run's always pretty easy. Minus a minus becomes what? Plus. So what is 7 and -2.5? We might pull out our calculator, but 5.5? I think it is. Okay. These ones, you could use your calculator if you know what to type in your calculator. And I did show how to use the calculator on the video you guys are going to watch tonight. Well, let's try to do it without it and see where we get. So if I put -2.5 in, which function am I on? You can go back to your picture again if you like. Or you can look here. It's this one though, right? The cosine graph. I kind of know what it is from the picture, so I'm not even going to bother plugging in. What is it from the picture? What's the y value there? -2, yes. And at -7, I'm going to be on this function. So I could put -7 in there. We weren't really sure how high. I think we had it. Didn't we have it a second ago? Did we calculate what it was? What was it? You guys have it on the front? I can do it again. It wasn't a -10? So you could actually plug it back in. I think you get -10 out though, if you do that. So again, we've got minus a minus. That's plus. That's 8. 8 over 5.5, what is that? It's kind of sloppy. It's like 1 point. You guys tell me? Quick, you guys should all be able to answer that real quick. Wake up. What is 8 divided by 5.5?
1.45.
There's Nick's 1.45, and that's positive, and that kind of looks like a slope of 1 to me, so it looks good. Okay, so there you go. That's it for that one. Stop this.